NASA is planning to continue exploration on the moon after confirming the existence of ice water. Our goal is to design a novel heating system for the battery of a lunar rover. The final design adopts basic chemistry principles to produce heat. The rusting of fine iron wool generates heat that is used to warm the battery. It is important to note that iron only rusts in the presence of oxygen and water. The system kicks into action when the temperature sensor attached to the battery falls below 5 degrees Celsius. The sensor sends a signal for the solenoid valves to open, releasing the reactants into the reaction chambers. Next, the reaction starts generating heat, which is transferred to the battery through conduction. Once the battery's temperature sensor rises above 5 degrees Celsius, the solenoid valves shut off. The final assembly consists of the oxygen distribution system, the water distribution system, and the failsafe system. As the oxygen enters the chamber, it encounters stripped iron wool and starts the reaction. The circles embedded in the iron wool are temperature sensors to monitor data. Water is dispensed from a water tank into a DC pump, which distributes the fluid across all 4 chambers passing through the water solenoid valves. Once inside the chamber, the water is finally misted into the stripped iron wool. Attached to the inner upper part of the reaction chamber, one can locate a humidity sensor for data acquisition purposes. If the temperature is too high inside of the reaction chambers, the solenoids shut off immediately and the reactants are channeled to the failsafe system. In order to create a prototype of the reaction chamber, a scaled-down version was designed and assembled. The oxygen is distributed to the system in the same fashion as the final design, however a manual valve was used instead of a solenoid. The same goes for the water distribution system, where water is fed by a DC pump into the chamber where misting nozzles disperse the water evenly on the iron wool. 3 types of sensors are used for data acquisition within the prototype: the humidity sensor, the pressure sensor, and the temperature sensors. A low vacuum packing chamber was designed and created to remove the protective coating from the iron wool and pack it inside the reaction chamber. In order to visualize the effects of ambient cooling on the system, as well as the heat generation due to the exothermic reaction, a transient thermal finite element analysis was conducted using ANSYS Workbench. The geometry of the model consists of the battery surrounded by 4 adjacent reaction chambers, sitting atop a layer of MLI and the rover body. The thermal loads applied are a constant internal heat generation within the iron wool, as well as a constant temperature of negative 230 degrees Celsius at the bottom surface of the rover body. In order to visualize the effects of ambient cooling on the system, as well as the heat generation due to the exothermic reaction, a transient thermal finite element analysis was conducted using ANSYS Workbench. The geometry of the model consists of the battery surrounded by 4 adjacent reaction chambers, sitting atop a layer of MLI and the rover body. The thermal loads applied are a constant internal heat generation within the iron wool, as well as a constant temperature of negative 230 degrees Celsius at the bottom surface of the rover body. What we were able to accomplish through our project is the design of a novel system that not only weighs less than 10% of the rover's weight, but also delivers 1.024 watts of thermal power per kilogram of mass added. Additionally, our system is reusable and simple to maintain and repair.